And that's a good moment for a hint, and that could be Monday. If you look, I'm going to post the homework on today. So by Monday, you can just read the questions, make sure you understand them, and I'm happy to start giving you hints, and then I think it's going to be a much more pleasant experience. So, yeah.
Yeah, Ziegler has a paper in archive that effectively proves things that.
Yeah. I mean, that's the other thing that I told you guys, and I mean it, that everything is fair game as long as you show me that you understand your answer. So if you Google and find some hints on Google, or even find the proof on Google, I mean, I don't want you to copy it, but if you prove to me that you understood it, then that's fine. That's full credit. Yeah. I really want you to know that I'm with you and not against you on this, and
I think a lot of us are stubborn and we're trying to figure them out for ourselves before we come to you, and so we wait till the end. After we've been beating our heads against it for a week and a half.
Yeah, I understand that.
Probably some of these are so hard and probably a little late to come to you.
Yeah. Okay. I think that he talked already, right? Yeah. I think he turned the volume down after the colloquium. Okay. So we're talking about graphs of polytopes, and I told you a little bit about linear programming. And what I want to do to begin with is just to talk about, just to give you an example of how you turn a question that looks like it's not about polytopes into a question about polytopes, which is how a lot of this theory got developed. Okay. So let me start with an application of linear programming. And let me just remind you that linear programming is the problem of maximizing a linear function c dot x over a polytope ax less than or equal to b. So how is this applicable? Well, let's talk about the following question. Let's say that you have a graph. Okay. So you have a bunch of vertices and a bunch of edges. Okay. And you should really think of this in very concrete terms. I don't know. You can think that these are cities. And these are roads. And or maybe let's say that these are kind of houses and internet cables, okay? And maybe you're supposed to, maybe this was an internet network, but then it completely fell off, it crashed, and now you have to rebuild it, okay? And so your goal is the following thing. Your goal is basically to at least manage to connect the whole network, okay? Goal. And the way you do that is that you're going to rebuild some of the edges to connect the network. Find a subset of edges connecting the network. Okay. So let me give you an example. You might rebuild this connection, and then this connection, and then this connection, and this one, and this one, and this one, and this one. Okay. And then once you do that, then there is maybe a roundabout way of going, but there's always a way of going between any two vertices. Okay. Now, presumably you want to do it in the cheapest way possible. Okay. That definitely seems to be the algorithm Comcast is using in my neighborhood. because certainly feel the roundabout. I guess that's on video. I shouldn't say that too loudly, but anyway, I'm sure they know. So then, of course, one thing is that you wouldn't. Once you have it like this, then since you're very cheap, you wouldn't want to build any extra edges because things are already connected. Okay, and so then what you're building is what's called a spanning tree. A spanning tree is a way of connecting all the vertices without forming any cycles. Okay, so this is what's called a spanning tree. Okay, and so this is called the minimum spanning tree problem. But of course, you cannot give me the answer to this problem until I tell you what it means to be cheap or expensive. And so the way we're going to do that is that you're going to have some cost associated to every edge. Okay? So there's a cost function from every edge to, I don't know, let's say the reals. Okay? So, I don't know, maybe it costs, I'll just put some numbers here. So these are the costs according to some unit. Okay. So this is my cost function C. So that's the problem. Is it clear what I'm asking? I hope you agree this is a very, very concrete problem, very practical problem that people will actually want to solve. Now you can stare at this and you can already tell me, is this or is this not the best solution? It's not. Why?
Because you could switch from having the 3 connection to the 1 connection.
So for example, instead of using this edge that cost me 3, you could use this one that costs 1. Okay, so you wouldn't want to use this one. Or instead of using this 5, you would rather use this 4. So clearly this is not the optimal solution. The question is, how do you find the optimal solution? And if you try to do it combinatorially, you could do what I'm saying. Kind of say, okay, well, instead of this 3, maybe let me erase it and build the 1, and then do something. Okay? But the point that I want to make is that actually this is an example of a question in linear programming. Okay? So my point is that there is a polytope that encodes this story, and that polytope is, we're going to call it the spanning tree polytope. Spanning tree polytope. Let's call it ST of G, and it lives in R to the edges. Okay? And the spanning, so what I'm going to do is that for each spanning tree T, I'm going to build a vector, and I'm going to call it chi sub T. Okay?
Sorry to interrupt. Notational question.
Yeah.
I've seen that a lot before where you say it's R raised to the E. I always want to think of that as R raised to the order of E. But they use R to the E. Is it like it's like the seminal functions out of E or something like this?
Yeah, that's a very good point. So actually, and I think it's the first time that I do it in this class. So in this class, we've set R to some integer. And here, I'm saying R to the E, where E is the set of edges. So you can effectively think of this as R to the number of edges. So if there's 10 edges, this is R10. But the convenience of this notation is that it canonically labels each coordinate with one of the edges. Okay? And if you remember what this notation means, it means exactly what you're saying. Functions from E to R. So what you're saying is to each edge, you're assigning a real number. So this notation matches the usual notation that we have for this kind of thing. But effectively, you can think of it as R to the number of edges, okay? But then the point is this, that I want to define a vector in R to the E, right? And so what I'm going to do is define a coordinate by coordinate. Okay, so each coordinate is labeled by one of the edges, and that coordinate is going to be 0 if the edge is not in T, and 1 if the edge is in T. Yep.
So we could use the fact that there are trees to limit ourselves to b-1 tuples.
No, you want them to be e tuples.
Oh.
So let me. I think this is going to be.
Sorry, you just defined it. Okay.
Yeah, I think it's going to be a little bit clearer if I do this in an example. Yeah, exactly. So, for example, if my graph is this one, okay, and maybe let's call the edges A, B, C, and D. Then how many spanning trees are there? Well, basically choose any 3 edges, and they're going to be a spanning tree. So, for example, here's a spanning tree: A, B, D. So this is T. And so I'm assigning to it the characteristic vector. This is called a characteristic vector, which just keeps track of what edges are in there. So A is in the tree, B is in the tree, C is not in the tree, and D is in the tree. Okay? So what I'm doing is just encoding my tree with a bunch of zeros and ones that tell me which edges are in and which edges are not in. Okay? This is a very common construction. It's good. It's good for you to get used to it. This is called a characteristic vector. It's a very common construction for taking combinatorics and turning it into discrete geometry. Okay? And then the spanning tree polytope is going to be the convex hull of these guys. So the spanning tree polytope of G is the convex hull of the characteristic vectors of the spanning trees. Okay. This says spanning tree polytope of G is the convex hull of chi sub T, where T is a spanning tree of G. Okay. So for example here, the spanning tree polytope of this graph is the convex hull of, now let me be lazy and just write this as 1101. So then what are the spanning trees? The spanning trees are A, B, C, and not D, A, B, not C, and D, A, not B, C, and D, and not A, B, C, and D. Okay, so they're basically all the triples in this case for this graph. This is a polytope in 4 dimensions. Okay. And the nice thing about this is that now, if you think of our cost function is a function from E to R. And a function from E to R is the same thing as a vector in R to the E. Okay? So for example, if I had a cost function here, so let me put it here in, what's the color of this in English? Aqua? So my cost function is going to be 1, 2, 2, and 3. Agua marina. A little bit more. Yeah. So that's a cost function, but then I can think of this cost function as being the vector 1, 2, 3, 2, right? And it's basically a vector in this space. And so really, what I have is some polytope, okay? And I have some vector that's a cost vector. And then if you think about it, you'll see that finding the optimal spanning tree is exactly the same thing as finding the optimal vertex in that direction. So if I have my cost function, basically I can think of it as living in R to the E, okay? And what's the cost of a tree T? Well, you see, if you take the dot product, for example, what is the cost of this purple tree here? It's exactly the dot product of the vector 1, 2, 3, 2 with the vector 1, 1, 0, 1. Because it says take the cost of the edges which are in T and don't take the cost of the edges that are not in T. So the cost of the tree T is exactly the dot product of C with the characteristic vector of T. And so what that means is that the minimum spanning tree problem is the same thing as finding the minimal phase of the polytope spanning trees of G in direction C. Okay? And so that rephrases this combinatorial problem into a problem about a very concrete polytope, the spanning tree polytope. Okay? Do you guys have any questions about that correspondence? Yep. So so let me say this again. The minimum spanning tree problem is asking me to find out of all the spanning trees, what is the one of minimal cost? Okay? But then what I'm saying is that the spanning trees correspond precisely to the vertices of the polytope. Because for each spanning tree, I built a vertex. And then the other thing that I'm saying is that if I want to find the cost of a certain tree, for example, the cost of this purple tree here, that's the result of taking the dot product of the cost function, which is all of these numbers. 1, 3, 4, 2, 3, 4, 3, 1, 2, 5, 4, 3. So that's the cost function. And taking the dot product with the edges that are actually in the tree. So this 1 is in the tree, this 3 is not in the tree, this 4 is not in the tree, this 2 is in the tree, this 3 is in the tree, this 4 is not in the tree, this 3 is in the tree, I think I missed one. This 1 is not in the tree. Yeah? Oh, yeah. This 1 is not in the tree, this 2 is in the tree, the 5 is in the tree, the 4 is in the tree, and the 3 is not in the tree. So I'm saying that this combinatorial notion of the cost of a tree is the same as the geometric notion of taking the dot product of my cost function with the characteristic vector of my tree. And so then what that becomes is that, I basically have this polytope, the spanning tree polytope, where every one of these vertices corresponds to the characteristic vector of one of the trees. So maybe if you have 4 spanning trees, then 6 spanning trees, then this polytope is going to have 6 vertices. And then the cost function tells you that you're pointing in some direction. And so what I'm asking you to do in geometric language is just finding in this case, the cheapest So the lowest cost. So in this case, it's this vertex, which is the cheapest according to direction C. So that's rephrasing the combinatorics into discrete geometry. But then the great thing is that now we have these geometric tools to carry this out. Okay. So if you remember what we did with Danzig's algorithm, is we said that you just start at some tree, you just choose some random tree. Maybe you chose this one. Okay. And then you say, okay, well, that's not the cheapest one, so that means that one of the neighbors has to be cheaper. So let me go to the neighbor, to some neighbor. That's not the cheapest one, so let me go down to another one of the neighbors that's lower. So maybe this neighbor is lower. That's not the lowest one, so then maybe I'll go to this neighbor, which is lower. And so that's geometrically what you would do. Okay? You just kind of flow down according to the direction C, as we did last time. Okay. So that's basically how you can bring linear programming into a lot of combinatorial problems. And I really cannot emphasize this enough, that one of the reasons that the theory of polytopes became so prominent is because all of a sudden with the appearance of computers, we can actually solve really big problems of this sort. And we can actually ask computers to perform the simplex algorithm for us, so we don't have to. And that really, I mean, this was really one of the big motivations in thrusting the theory of polytopes forward recently. Okay. Question? Comment?
How do we know that our cost function is in a different position?
That's a very good question, and we don't. So the question is, how do we know that the cost function is in general position? It might not be. It could be that all the edges cost the same, and if that's the same, then if that is so, then it wouldn't be in general position. But basically, Danzig's algorithm works, and the problem is that there might not be a unique bottom vertex. But you can still apply the algorithm and arrive to a unique lowest vertex that might not be the lowest one, but it would be an optimal solution. And if
Why would it be optimal if it's not a unique source?
well, because the thing is that if you really work for Comcast, you don't really care to characterize all the possible solutions. You just want to save money. So as soon as you found a cheapest solution, you're not going to ask any more questions. And there might be 4 cheapest solutions corresponding to maybe a lowest face with 4 vertices. But as long as they found one of them, they don't care. They're done.
All minimizations are going to be equivalent?
They're different solutions, but the cost is the same.
On the cost function.
Yeah. Yeah. Right. And I should tell you that basically whenever you have these kinds of questions where you're trying to optimize something and that something is given by some linear function in something, generally you can do this trick and if this kind of thing interests you, I can point you to a beautiful book. It's actually a series of books called Combinatorial Optimization. Each one is about as wide as the Bible, and there's 3 of them. And it's really an amazing book. It's very encyclopedic, and it really does this for a lot of different actual problems. Shriver's books. But this is just to give you an idea. Okay. Now, one thing that I should tell you is that one reason that we can do well here is because we understand this spanning tree polytope. Okay. So, of course, you have this general problem of linear programming, but the more that you know the polytope you're playing with, the more tools you have. And so, when you have something like this, like a spanning tree polytope, then one thing that you have to wonder is, can I understand that spanning tree polytope? Because if I can, that's going to give me more tools. What do I mean by understanding? I mean, for example, what you did with the permutahedron in the homework. Okay, so I define the permutahedron as some convex hull, but you stare at it long enough that, for example, now you know what the edges correspond to. The edges correspond to swapping two adjacent numbers, which you might not know a priori. Okay? And so you might ask the same thing about this. How do I know what this polytope looks like? And it turns out that you can say, and it's very nice. So here's a nice fact about this spanning tree polytope, that the edges of the spanning tree polytope look like this. So you have an edge between two trees. If and only if you can obtain the tree T prime from the tree T by deleting one edge and adding one edge, which is precisely the kind of things we were doing here. Here we were saying, okay, why do I know that this is not optimal? Because I could delete 3, I could delete this edge, and I could add this edge. And my point is that what you're doing there really is going from one vertex of the polytope to a neighbor vertex. That's exactly what neighbor vertices correspond to swapping two edges. Okay. So T prime is equal to T minus an edge plus an edge. Maybe it's easier if I draw a picture. So here's what a general tree kind of looks like. So maybe this is T. So so this corresponds to a vertex of the spanning tree polytope. If you want to know what the neighbors of this guy are, then what you have to do is look at all the ways of deleting one edge and replacing it by another edge. And that's going to be a neighbor vertex. Okay. So this is what I'm calling E, and this is what I'm calling F. Okay. So that's a beautiful polytope. It's a beautiful polytope where you can describe the edges very exactly. Okay. And what turns out, so another fact that's a consequence of this, is that if you want to get, I mean, let's think about this. How big is this polytope? How many dimensions does it have? The dimension. So you're answering a different question, which is my next question. But the dimension. What dimension does this guy live in? E, right? The number of edges, because it lives in R to the E. At least, let me say that this is, so it lives in E dimensions. It turns out to be E minus 1 dimension. And if you think about why that is, for example, this polytope actually, even though it lives in 4 dimensions, it's 3-dimensional because it lies on the plane A plus B plus C plus D equals 3. And that's always true in general, that these polytopes live in a plane x1 plus x2 plus x3 and so on equals something. So it's in dimension E minus 1. How many vertices does it have? So I think that's what you were going to answer. It's the number of spanning trees, right? Well, assuming that these are all vertices, which is true, the number of spanning trees of a graph. Do you guys know anything about the number of spanning trees of a graph? So you guys are telling me different answers that all amount to the same, which is that it's a lot. Now, how many? Let me give you an example. The number of. So here's a really nice theorem, beautiful theorem in combinatorics. The number of spanning trees of the complete graph. Does anybody know what this is? It's even more dramatic than that. It's n to the n minus 2. And the complete graph is basically where all you have n vertices and they're all connected to each other. That's a lot. That's a lot of vertices. Okay. So think about it then. Is this a practical algorithm? When you have a polytope that has n to the n minus 2 vertices, that's a lot of vertices, and you're somehow supposed to find the best vertex. Well, in principle, it sounds like it shouldn't be, but it turns out, because of this, that the distance between any two vertices is at most n minus 1. And you should be shocked by this, because this is a lot of vertices. And I'm telling you, even though there's so many vertices, they're all very close to each other, you can really, they're very connected. So the point is that this is a lot, right? And this is a more precise reason for why that's a lot. I actually just switched. I just ran out of battery here.
Everything has connectivity 2 with the end with connectivity 1, which would be distance of n minus 1.
I think the answer that I have to your comments is that actually this is a homework problem, so you're going to understand this very well in 2 weeks, and you're gonna agree that it's not obvious, and you're going to understand why it's true, and it's actually not too hard to prove once you know this. Okay, but anyway, so the point is that the maximum distance between two vertices and by distance I mean edge distance, right? So how many edges do you have to walk to get from one to the other one? Is at most number of vertices minus 1. Shocking. I think this is shocking and beautiful. And what that means is that actually this problem you can solve very quickly. But only because of this. But if I give you a random polytope, actually, it's too hard to do in practice. So this is kind of what linear programming feels like. Linear programming, in principle, we have this algorithm. In practice, we don't know if this algorithm is going to work. But in a lot of the actual applications, like this one, it turns out that linear programming works beautifully. And it's kind of a mystery why it works so beautifully. Not kind of, actually. This is one of the big open problems in this field. Why does linear programming work so well? But this is the kind of reason why it works so well, that things behave unexpectedly nicely.
It's the same result as the underlying graph. I mean, this is the max distance between two vertices. I mean, the vertice is spanning tree, and the maximum distance between two spanning trees is the same as. So when you say v minus 1, what do you mean by v? Is that v as in your vertex set of spanning trees, or your vertex set of your underlying graph?
So what I'm saying here is that, right? So, yeah, I see why you're confused, because I wrote vertices, and these mean different things. So here I meant vertices of the polytope of spanning trees. And so what this means is the distance between two different spanning trees. And what I'm saying is that in this big polytope, you can change from one spanning tree to the other one in only v minus 1 steps, where v is the number of vertices of the original graph.
Yeah,
and that's cool. The other thing is not cool at all, I agree.
Can we say something stronger to give the exact distance between any two vertices of our spanning tree?
Not in general, I think.
Okay, so we can't say that there's, I guess, v minus 1 minus the number of edges in their intersection.
Oh yeah, I mean, in this case, yes. Yes, that's true. So in this case, actually, you can say for any two vertices, you can actually say combinatorially what the distance is for this concrete polytope. That's true. And again, you'll understand this very well very soon. Now, here's where, so let me just make some general comments about this. So how good is linear programming? In theory, we don't really know. But in practice, it seems to work very well. Okay, let me say often very good. What I mean by this is that linear programming is one of different methods that you could use for optimization. It's kind of one of the oldest methods, and since then, fancier methods have been developed, and yet linear programming often seems to be the best one, even though it's one of the more basic ones. Now, hopefully you see from this that this question is related basically to how far vertices are from each other in these polytopes. So this is related to the following question. Let's say that you have P as a polytope. Then I'm going to define the diameter of P. And the diameter is going to be the largest distance between two vertices of P. Largest edge distance between two vertices of P. So for example, if a polytope has diameter 5, then what I'm saying is that you can walk from any vertex to any other vertex taking 5 steps along edges. Okay? And so the question is basically how large are the diameters of polytopes?
So you're given the value of, for a given polytope, you're given the value of an edge to be 1. Any edge of any size.
Right. So when I say edge distance, I just mean how many edges do you have to cross to get from one vertex to another. So the question is, how large is delta of P? Okay. And if delta of P is small, then we have some evidence that these algorithms will work well. Okay. Now, of course, this answer depends on P. And so let's fix some parameters. And so the way that people normally do this is that they define this number delta D of n to be the largest diameter of a D polytope with n facets. Okay. So out of all the polytopes that live in D dimensions and have n facets, what's the largest possible diameter that you see? And the idea is that if this is small, so let me say a specific conjecture. Delta of D comma n is less than or equal to a polynomial function in D and n. So if you could prove this conjecture, then you would have some evidence that there might be polynomial time algorithms here, that linear programming could work in a polynomial time. This conjecture is wide open. No one knows if this is true or not. Okay? But actually, people are much more optimistic than this. And here's a conjecture. This conjecture is due to Hirsch in 1957. And this conjecture says that not only is this true, but actually it's this. this is kind of a big conjecture, and this is a much more concrete conjecture. Okay? So not only is it a polynomial, but it's actually a linear polynomial, a very small polynomial. Yep?
The first conjecture was proved in May.
Yeah, that's what I'm going to tell you.
Oh, okay.
Okay. Thank you, though. Yeah, so I mean, this is why I want to talk about this, because actually this was open for 53 years, and it was just settled this summer. And so this is a theorem due to Paco Santos. Actually, you were probably at Davis at the same time as he was.
He taught my number theory class in undergrad.
So Paco Santos is kind of a friend of the Bay Area discrete math community, and he just proved that this is not true. This is false.
There must have been some proofs along the way, though, for the Hershey conjecture that it's true over some very large types, right?
Yeah, so I want to tell you more about this. So, for example, people had proved that there's a reason for this bound. There's a reason why people thought that n minus d might be the right bound, because they could prove it for several families of polytopes. So, for example, if the dimension is small, this is true. Small, I think, means dimension up to 5 or 6 people know that this is true. Also, if n minus the dimension is small, then people had proved this. Let's talk about something. Imagine that you wanted to disprove this conjecture. So you wanted to find a polytope with a very large diameter. So where might you look for a polytope with large diameter? What's a very extreme polytope? So the cyclic polytope is extreme in kind of the wrong way. So why is that? Because in the cyclic polytope, every 2 vertices are connected. So this is somehow the extreme in exactly the way that we don't want it to be. But then if you take the dual of that guy, then maybe that's where we should be looking for a counterexample. And so people tried that, and actually they proved that the dual of the cyclic polytope satisfied this. And so then they thought, okay, well that's some more evidence. And so what I want to discuss, I think I'm not going to finish today, but I want to tell you basically some evidence for why this conjecture is true, but then I'm going to show you that the evidence is not good enough because the conjecture is not true. Okay. So why? So by the way, Paco Santos is amazing, and what he found is a polytope in 43 dimensions with 86 facets, having diameter at least 44. And he's amazing at this, and I want to tell you a little bit about how. I mean, the point is not really that he can see polytopes in 43 dimensions, but that he's, I think, one of the world experts at building high-dimensional polytopes with very extreme properties out of things that we can see in 2 or 3 dimensions. And so really, the pictures that he was staring at to get this proof are actually 3-dimensional pictures. And I want to explain to you how it's actually out of 3-dimensional discrete geometry that he managed to build this polytope that lives up in a lot of dimensions. But another thing that I want to point out to you is that, and he says it himself, that this is really just a drop in the bucket, and I mean this is kind of bad news. But it says nothing about this, and the best thing that he can prove is he can find polytopes for which this bound is 1.005n, I think, something like that. So it's conceivable, for example, that this is true if you put a 2 in front. And if it is, then for all practical purposes, it's effectively the same thing. It's more like a psychological barrier because people thought that this was the way to prove it, this was the right bound, and this is just not the right bound.
But since this is such an applied part of discrete geometry, I mean, everyone just goes on their merry way using the algorithms because they know they're going to work every time.
Yeah. Yeah, it is true that, I mean, in practice, you might say that people who actually use this don't even care about this because as long as they run the algorithm and the algorithm finishes, they're happy. But we're mathematicians, we want to know why things work. So we care about this. Okay, so maybe let me just begin by telling you, should I? Let's see. No, I think I don't want to rush this. I think maybe I'll stop here. I'd rather finish early instead of late. And next time I'll just begin by telling you a little bit about how this was done. And by the way, obviously, I'm not going to give you the full proof. And I think a very nice project would be to understand his proof. And his proof is actually, it's a beautiful paper, and he has a bunch of expository papers about the proof. So I think it's actually not too hard to get a pretty good idea of what he did.